Now you will calculate the contribution to thermal conduction from electrons. And to calculate the heat capacity due to electrons, first we can start with classical treatment. The energy of a free electron gas, well, only has the kinetic contribution, so we can write this in 3 dimensions as translations in x, translations in y, and translations in z, giving us 1/2 m vx squared plus vy squared plus vz squared. Now we have 3 quadratic terms in this energy, 3 degrees of freedom, and the equipartition theorem tells us that each independent degree of freedom that gives us a quadratic term in the energy basically contributes 1/2 Boltzmann constant times temperature to the average energy. So because we have 3 quadratic terms, it will be 3/2 kT per electron. That's the average kinetic energy at temperature T. For capital N electrons, we have to multiply this by capital N, 3/2 capital N kT, and we will find that CV, with the derivative of the energy with respect to temperature at constant volume, is 3/2 nk. For 1 mole, Na times K is universal gas constant, it will be 3/2 R, which is the molar specific heat. Now the experimental value, we find that for metals is almost a factor of 100 less, and it's typically temperature dependent, so this classical result does not seem to hold for metals at temperatures close to room temperature or low temperatures. So we need the quantum treatment. In the quantum treatment, when an electron gas is heated from 0 Kelvin to temperature T, we need to calculate the increase in its energy. The 0 Kelvin energy is energy density of states times dE, integral from 0 to E Fermi. So we are looking at the change in the number of electrons with energy, dN dE with dE, so that is going to give us the number of electrons per in the having the energy E. So we integrate over all possible energies from 0 to E Fermi. That gives us the total ground state energy of the system that has capital N electrons. Now we have at a finite temperature a probability of occupancy of energy E, so we have to weigh this by this probability. That's the Fermi-Dirac distribution function. So all possible energies range from 0 to infinity, E dE, f of E dE. So this is going to give us the finite temperature energy. The total number of electrons will be the density of states, dN dE, multiplied by the Fermi-Dirac distribution function, the probability of occupancy of an energy E, and dE. So when we integrate this from 0 to infinity, this will give us the total number of electrons. Now the density of states with that changes with energy E is V over 2 pi squared, 2m over h bar squared to the power 3/2 e to the 1/2. So that's what we have found out in our previous calculation here for 3-dimensional electron gas. So we can substitute for Fermi-Dirac distribution function 1/1 plus e to the e minus e Fermi over kT. So we neglect the temperature dependence of the chemical potential and approximate it to be equal to E Fermi at temperature T. So here is mu of T for regular temperatures is very close to the Fermi energy. And we define this constant in the density of states that shows us the proportionality constant K, where the energy dependence is e to the 1/2. K is V over 2 pi squared, 2m over h bar squared to the power 3/2. And the ground state energy, therefore, will be the integral from 0 to E Fermi, E dE dE, here actually you could also put Fermi-Dirac distribution function, but Fermi-Dirac distribution function is equal to 0 at T is equal to 0 Kelvin, so in the ground state. So you will have, for the density of states, we have the constant K, integral from 0 to E Fermi e to the 1/2 from density of states, and E in the integral, so E to the 3/2 dE. So that gives us 2/5 K times E Fermi to the power 5/2. So if you substitute for K, V over 2 pi squared 2m over h bar squared to the power 3/2, the 2's cancel, and we find that the ground state energy is V over 5 pi squared 2m over h bar squared to the power 3/2 E Fermi to the power 5/2, and then, as expected, there is no temperature dependence. It's the 0 Kelvin total energy of the system. Now, for the finite temperature energy of the system, integral from 0 to infinity, E dE, f of E dE. So, for the density of states, we substitute K e to the power 1/2, E f of E dE. So that is going to give us K e to the power 3/2 Fermi-Dirac distribution function dE, integral from 0 to infinity. And once again, we have for n, the total number of electrons, density of states, Fermi-Dirac distribution function dE from integral from 0 to infinity. So we're going to play a trick here in order to calculate the heat capacity. So this integral for capital N, we multiply with the Fermi energy. So we're going to take this expression and multiply it with the Fermi energy. That gives us E Fermi times N is equal to integral 0 to infinity E Fermi d of E f of E dE. So the heat capacity will be the derivative of U with respect to T. So you can see that there is no temperature dependence in ground state energy. So it's the finite temperature energy change with temperature. That's what we're considering. So del U del T. The density of states has no temperature dependence. Density of states E del F del T dE. And on the other hand, if you look at the integral for E Fermi times N, when you take the temperature derivative with respect to temperature, that should be 0 because E Fermi times N is a constant. You would have E Fermi density of states, which is not temperature dependent, derivative of Fermi-Dirac distribution function with respect to temperature, dE. So if I subtract these two integrals, C minus 0 will be integral from 0 to infinity density of states, E minus EF, dF dt, dE, and that's going to give us the heat capacity. So obviously I need to know the derivative of Fermi-Dirac distribution function with respect to temperature. So that is d dt of 1 plus e to the minus e Fermi over kT minus 1. Once again, this is actually E minus mu, but I neglect the temperature dependence of chemical potential and set it equal to Fermi energy at 0 Kelvin. So this is going to give me minus 1 plus e to the minus e minus e Fermi over kT parentheses squared, and e to the minus e Fermi over kT, and from the derivative of the power of e, I will have minus e Fermi over k T squared with respect to temperature. So the minus signs will cancel, and dF dt I found to be E minus EF over KT squared, e to the minus E minus EF over KT, parentheses 1 plus e to the minus EF over KT squared in the denominator. And now I'm going to substitute E minus E Fermi over KT is x, and dE is then KT dx. Okay? dEF is 0. So del F del T then is going to become E minus EF over KT, that's x divided by T, because there's a T square here, e to the x divided by 1 plus e to the x parentheses squared. So I ask myself which energies are meaningful. So at low temperatures, KT is much less than 0.01 E Fermi. So we will find that low temperature here means For 0.01 E Fermi over K, it's roughly around 500 Kelvin. So when we talk about room temperature, slightly higher temperatures or lower temperatures, we are always in the low temperature regime. So we're not talking about energies smaller than E Fermi, all states are occupied. And if the energy is much greater than E Fermi, we would find x goes to infinity, and the limit as x goes to infinity, this derivative df dt, is x over t e to the x over 1 plus e to the x parentheses square, which is an infinity over infinity case. So we use L'Hopital's rule, take one derivative, e to the x plus x e to the x divided by 2t e to the x 1 plus e to the x. E to the x's cancel, and we have again infinity over infinity. So one more derivative gives us 1 over 2t e to the x, which is 0. So the derivative del f del t is large only at energies close to the Fermi energy. When we go far away from the Fermi energy, the derivative becomes 0. So only energies close to the Fermi energy are meaningful. So we can say that the thermal energy, which is, for example, at room temperature 0.026 eV, is very small compared to the Fermi energy, which is 3 to 5 eV. For this calculation, only energies close to the Fermi energy are meaningful. So therefore, instead of considering density of states, we can replace it with density of states at the Fermi energy. So C will be integral from 0 to infinity, density of states at Fermi energy, E minus E Fermi, del f del t dE. For del f del t, we substitute x over t, e to the x over 1 plus e to the x squared dE. And for E minus E Fermi, I can substitute kT times x. For dE, I can substitute kT dx. So that's what I did here. So this will be density of states at Fermi level, kT parentheses squared over t integral from minus E Fermi over kT. So that is when the energy is 0, x is equal to minus E Fermi over kT, to infinity. X squared e to the x dx over 1 plus e to the x squared. So since E Fermi is much greater than kT, minus E Fermi over kT is a large negative number, so we can approximate it as minus infinity. So the heat capacity will be then density of states at Fermi level. Now I had kT squared over t, so that becomes k squared t integral minus infinity to plus infinity x squared e to the x over 1 plus e to the x squared dx. So you can look up this integral from integral tables. It has a value pi squared over 3. So we find that the heat capacity should be density of states at Fermi level, k squared t pi squared over 3. Now I need to evaluate density of states at the Fermi level. It is V over 2 pi squared, 2m over h bar squared to the 3 halves, E Fermi to 1 half. E Fermi was h bar squared kf squared over 2m. Kf was 3 pi squared capital N over V to the power 1/3. So E Fermi, I find h bar squared over 2m, 3n pi squared over V to the power 2/3, because it's kf squared. 1 over the Fermi energy is 2m over h bar squared, V over 3n pi squared to the power 2/3. And if I take 1 over the Fermi energy to the power 3 over 2, I find 2m over h bar squared to the power 3 over 2, V over 2 pi squared multiplied by 2 over 3n. So this is basically the density of states at the Fermi level multiplied by E Fermi to the power minus 1 over 2. So that's the part I see here. So the density of states at the Fermi level will become E Fermi to the power 1/2 times E Fermi to the power minus 3 over 2 and 3 capital N over 2. So we find that density of states at the Fermi level is 3N divided by 2 E Fermi. Okay. So we can go back to the heat capacity. So that's going to be density of states at Fermi level k squared T p square pi square over 3. So we can substitute for density of states at Fermi level 3N divided by 2E Fermi, k squared T pi squared over 3. The 3's will cancel, so I find that the heat capacity is 1 over 2 pi squared k squared Tn over E Fermi. Now, if we define Fermi temperature as Fermi energy equals to K times Fermi temperature, you can find that a typical value of Fermi temperature is 5 eV over 8.6 10 to minus 5 eV per Kelvin. So it's going to be 58,000 Kelvin roughly. So it's a huge number. So if I substitute for E Fermi K times T Fermi, one of the K's will disappear, and I find the heat capacity to be 1 over 2 pi square K capital N T divided by T Fermi. So as a result, I find that the classical heat capacity was 3 over 2 capital Nk. Quantum mechanical treatment gives me a temperature dependence, pi squared over 2 capital Nk, T over Tf. So it's linearly dependent on temperature. If we take the ratio, we find that the ratio is T Fermi over 3T, or quantum mechanical result is 3T over Tf times classical result. So when we have 3T is equal to the Fermi level, Fermi energy, which is about Fermi temperature, which is about 60,000 Kelvin, we find that the classical and quantum mechanical results will be the same. So we need temperatures of the order of 20,000 Kelvin for the classical result to hold. And at room temperature, the quantum mechanical heat capacity is 3 times 300 divided by 60,000 times classical result, which is 1% of the classical result. That's experimentally what we observe. So we can now talk about the thermal conductivity. The thermal conductivity for electrons will be, contribution from electrons will be 1 over 3 CV V Fermi times L. So it's those electrons that are close to the Fermi level that are carrying the energy. So we consider the Fermi velocity. So it will be 1/3 V Fermi times L, the mean free path, times the heat capacity per volume. So we substitute pi squared k squared over 2 Tn over EF times 1 over the volume. And for E Fermi, we can substitute 1 over 2 mV Fermi squared, where the V Fermi is L divided by tau. So it's the mean free path divided by the mean free time. So basically, it's we're considering the Fermi velocity to be close to the average velocity here. So with that simplification, we obtain an electron contribution to thermal conductivity, pi squared k squared over 3m tau n t, where n is our number density, capital N divided by V. So the thermal conductivity will have contributions from phonons and electrons. In normal pure metals at room temperature, kappa is 10 to 100 times those of insulators. The dominant contribution is from electrons. The phonon contribution will become important in insulators and also in impure metals. Now we can summarize what we did here. We considered the heat capacity due to electrons using equipartition theorem and 3 independent degrees of freedom giving us 3 quadratic terms. We found 3 over 2 R as our molar specific heat. Then we used the quantum treatment. We have to find the derivative of the total energy with respect to temperature at constant volume. In order to calculate the total energy at a finite temperature T, we need to look at the contribution to energy from each electron, density of states, probability of occupancy of that energy level, times dE, integral from 0 to infinity. If you subtract from this the ground state energy, we obtain delta U, but the ground state energy does not depend on temperature as we have shown here. So the derivative will be only for the finite energy contribution T. And the total number of electrons is given by the integral from 0 to infinity, density of states, probability of occupancy, Fermi-Dirac distribution times dE. So we have played a trick here. We multiplied the total number of electrons with Fermi energy, and then we subtracted the derivative of finite temperature energy U with respect to T from 0, which is the derivative of EFN with respect to T. This makes us our calculation easier, and we have defined E minus EF over KT as X, and with the simplification that the meaningful energies are close to the Fermi energy, we have replaced the density of states with a constant value at the Fermi energy, and we have performed the integral from minus infinity to plus infinity because the x lower limit minus EF over KT is a large negative number. We have found an approximate answer, density of states at Fermi level, k squared T pi squared over 3. We have evaluated the density of states at the Fermi level from our previous results. We found 3n over 2e Fermi. And finally, we find that the quantum treatment gives us a heat capacity that is linearly dependent on temperature. In fact, it is controlled by temperature T to Fermi temperature TF ratio. And we find that at room temperature, the quantum mechanical result is 1% of classical result, which is the experimental value, and 20,000 Kelvin is when the classical result would hold. And finally, we have calculated the contribution from electrons to thermal conduction, and we found that we have basically 1/3 CVVF times L, because we're considering the electrons that are close to the Fermi level, so the Fermi velocity VF here, and we find that this contribution is dominant in pure metals and 10 to 100 times larger than the insulators. And the temperature dependence that appears from this treatment is proportional to T, but we have to be careful about temperature dependence of tau here, so this is not a complete discussion in that sense.